An airplane. Shadow of an airplane. But what's cooler is what's going on around it. This is actually used to be a very rare observation called the glory. It's not so rare anymore. Up until very recently, scientists weren't even sure completely what was going on. We know that there is reflected light because the light is polarized. All right, polarized. You guys know about light? Light travels like a wave, okay? But not always like that. Sometimes it goes like this. Sometimes it goes on the angle. That's how light travels. But if light bounces off a surface, I don't care if it's going this way, it hits a surface and bounces, it's going this way. All right, if it came in on an angle, it hits, it's going, that's called polarized, when it's all the waves are lined up in the same direction. When light bounces, it becomes polarized. That's why polarizing sunglasses take care of and get rid of all that glare, because they take care of the light that's all bouncing the same way. Now, we know the sunlight coming through the glory, coming back from the glory, is polarized, which means sunlight has entered tiny little droplets. These are not crystals, these are droplets. It's bounced, but something else is going on. We're not sure what, that produces what looks like a tiny little halo centered around the observer. This is important. Where was my friend sitting when he took this picture? And don't say in the airplane, because obviously it's the shadow of the plane. Where was he sitting in the airplane? What part? Who? Around the wing. Right in the middle, because it's centered around him. If the pilot had taken this shot, it would have been up here. If the guy in the cheap seats in the back, it would have been over here. Long time ago, glories were incredibly rare. And I guarantee you, they also led to some really weird religions. Because back in the old days, we're talking old days, people used to, they'd climb to the mountaintop to meditate and be at one with the universe. I think it's to get a better view with their telescopes. But they're sitting up there, the sun comes up and it's kind of misty, and they're looking at the beautiful sunrise, and they look behind them, there's a halo around my shadow. I am the chosen one. Worship me and send me money. Meanwhile, the guy sitting next to him going, what are you, an idiot? The halo, that's around my head. It's centered around the observer. So I look back and I see it centered around me. This guy over here sees it centered around him. You know what? We're going to settle the argument. Stay there. You stay right there. I'll stay here. And we're going to hold the camera up right directly in the middle of us, and we're going to take a picture and see who gets the glory around our head. Click. Who gets the glory? The camera becomes the chosen one. It's all based on the observer. Ever since commercial airlines literally took off, glories became very common. If you are flying above a cloud deck, look down, opposite the sun. And this is where if you're flying west, get on the right side of the plane. All right, because as the sun is coming up on this side towards the south, you look out your window here, if there's clouds below you, you're going to find a glory. They are common and fun to see. This one, we were so high up above the clouds, you couldn't even see the shadow of the plane. But there it is. So they're out there. Look for them. They're cool. I got to be careful with this shot, especially if you guys are going to share these with other people. I think this slide was taken by Alan Dyer. But a friend of mine, and he writes for, astronomy or Sky and Tell, one of those. Oh, my, I'm going to get in trouble for that one. Alan is a Canadian, and he's a great guy, great astronomer, wonderful speaker as well. But a friend of mine who's a college professor used a bunch of pictures, and I think he stole them off like spaceweather.com, so he didn't give me any credit. But I remember seeing this shot, so I want to make sure Alan gets credit if he's listening. What are we looking at? Crepuscular rays. Crepuscular meaning towards the sun. Now, you've seen on a cloudy day where there's breaks in the clouds and the sunlight is coming through. Some people going, God's fingers coming through the clouds. Well, here the sun is setting. But there may be some mountains on the horizon, or there might be some really tall thunderheads. that give you these rays that come out towards you. They're spreading out as they reach you, and then as you turn around and look the other way, they come back together. They're actually parallel. They're going like this. But for you, the observer, they seem to spread out coming towards you, and then they come back together behind you. Towards the sun, crepuscular rays. Looking the other way, anti-crepuscular rays. Okay? Not anything particularly scientific, just cool, pretty, and now you know what's happening. Big clouds on the horizon creating those shadows. All right, this is where I get in trouble. Oh, who's going, why? What? Yeah, what is it? Yeah, a cloud. They're very common. Buy a big telescope. You'll see lots of transits. The clouds will all go in front of the stars for a month. Ahem. The Yaggers all know what this is. What's wrong with you people? The green flash. If conditions are perfect, as the sun is setting, the last bit that you may get is this emerald green. Now, if you saw Pirates of the Caribbean 3, no, it doesn't turn the world on its head and all that, but it can be really cool to see. And Steve O'Meara claims to see these all the time. And I used to tell people that, and he's a liar, because he also sees things in a 4-inch scope that don't exist. Mostly because I like picking on Steve, because he's a really good guy. The problem was, I have traveled all over I've been California watching sunsets. I've been to Tucson. I've been down here in the Keys, New Jersey. That doesn't seem to fit with all those other places. Anyway, I've traveled to a lot of places just to watch sunsets to look for the green flash. I've never seen one. And I've seen great conditions, never seen one. Then Lisa and I were on a cruise a year and a half ago. Yes! Saw the first one. This year I saw another. So Steve O'Meara, I apologize for all those times, including at the Texas Star Party when he called me up in front of everybody and I called him a liar there too. I didn't take the shot. Actually, this is one of Steve Matten's shots, who's our barking walrus. This is one of Steve's shots. It's a beauty, absolute beauty. The green flash is real. The last bits of sunlight being refracted, bent as they come in. The weird thing about this picture, where is the sun actually? Yeah, far away. Yeah, it's always far away. Where is the proper position of the sun when this picture was taken? What? Yes! Love you guys. The atmosphere. Notice how when the sun's high up, you don't dare look at it. It's too bright. When it gets lower, it starts to get bigger, and it gets redder, and you sometimes can look towards it. Well, there's a lot more atmosphere when you're looking along the horizon. But the atmosphere bends, refracts light. When the sun is sitting right here, it's actually already set. That beautiful sunset you're watching already happened. You're getting the replay. Okay? That's how much the atmosphere bends light. Half a degree. The sun when it's sitting, now this is half a sun, but if this were the sun right here, it's already there. But anyway, and if that green flash isn't convincing enough, a friend of mine who works out at the big solar telescope out in Tucson, Rob Sparks, he has a blog. If you look up Half Astro, he's got some of the most incredible green flash pictures taken from Tucson, from Kitt Peak. How about you got green flashes here, you got green flashes here, you got green flashes up here. He's got a shot that's got 5 or 6 within it. It's incredible pictures. I wish I remembered his full blog name, but just look up either Rob Sparks or Half Astro. It'll take you to his site. And then we get to everyone's favorite atmospheric, the rainbow. You've all seen one, right? The weird thing is, rainbows aren't that common. If you live in Hawaii, it's every day, because they have conditions there that there's always a rainbow somewhere in Hawaii. But the average person only sees 2, maybe 3 rainbows a year. But everybody's seen them. Everybody remembers them. They're beautiful. We love them. And what is a rainbow? The physics, of reflection and refraction of white light in a drop of water. So, with that, let's talk about some rainbows. Before I leave that picture up too long, why don't you put up another picture? Let me see what you got. Ooh, that's scary. What do I got over here? Yeah, that's a rainbow. All right. Before we get to the scary stuff, a little bit of history. People have seen rainbows forever. That's about as much history as you need to know. We haven't understood them, but people have always seen them and worshipped them, made up all sorts of myths. People didn't understand. They knew it had something to do with the sun and something to do with rain. But past that, they really didn't understand. You go back, there are cave drawings of rainbows. So, yes, we've recorded rainbows all through history. Now, if I were to say the year 1637, that sounds like a long time ago. But if you think about how long humans have been around looking at rainbows, 1637 is when we first began to understand them. See, back then, the best thinking was you got sunlight and you have raindrops of a certain size. Well, there was a fellow by the name of René Descartes. Now, he's known more as a philosopher, but he was a mathematician, a scientist, an astronomer. He was a bright guy. What is he known for? His big hit, I think, therefore. That's the guy. Well, René thought about rainbows a lot. And he thought it doesn't make sense that the size of the raindrop should really matter. So he made a big raindrop. And he did some experiments. Now, René knew about what's called the laws or the index of refraction. Starts to sound technical. Here it comes. That's this picture over here. Here we have a raindrop. Now, all these lines coming in, notice how they're all parallel, they're all lined up. They're rays from the sun. Let's look at ray number 1. It comes right into the middle of the raindrop, it hits the back, and it bounces straight back. Okay? That's easy. It reflects. Ray number 2 comes in a little bit above center. As it comes in, it's bent. It's refracted a little bit, just like your telescope. Refracts, it bends. See, I told you, you'd know it. Bends the light, hits the back of the raindrop, it reflects, and then on the way out, it's refracted a little more. Notice it started out that far away, it ended up out here. Ray number 3 comes in, refracts, reflects, refracts, a little farther out. 4, 5, 6, 7. 7 comes in, refracts, reflects, where's 7 over here? Out right here. Every ray that comes in after that winds up inside that ray. So let's take number 10 here. It comes in, bounces, refracts. Number 10, there's 7. 10 is here. Notice 8 and 9 out here. Wait a minute, I thought you said they're all on the inside. I did. If you follow those rays, they're going to cross number 7 and wind up on the inside. This is 42 degrees away from the straight back angle. Degrees, that doesn't mean 42 degrees. Oh, that sounds cold. You know, a circle, we chop up into tiny little pieces. Actually, 360 of them. There are 360 degrees in a circle. This is angle measurement. All right, so these are all angles here. I know you guys know it. I want to make sure everybody's with me. 42 degrees is as far away from the straight back as they will exit the raindrop. So the number 7 is called the Descartes ray because he discovered this. He also discovered that the rainbow appears about 42 degrees away from the anti-solar point or from the straight back angle. We'll get to that in just one more slide. But this whole line drawing here kind of caused some problems. To this day, we don't know if Descartes figured this out on his own or not. Because 30 years before Descartes published his work, there was a fella by the name of Snell. He was Dutch. And Snell had figured all this out. Now, today we know Snell probably did it first. But do we know? He never published his work. But today we talk about Snell's laws of refraction. unless you live in France, where they talk about Descartes' laws of refraction. Politics, it's everywhere. All right, let's go to the next slide on this one. So, the sun is up here. All these rays are coming in, all right? The sun's over there. I'm the observer. It's raining over there. Those are your ingredients for rainbows. It's as simple as that. If the sun is out over there and it's raining over there, you are going to see a rainbow. And here's the drawing of it, all right? 42 degrees away from the straight back angle, or the anti-solar point. Anti-solar point. How could you possibly figure out where is the spot opposite the sun? Can anybody not named Feller figure out where is the opposite of the sun in this picture? Correct, but where is that? Well, I'm not in the picture. Where? No, there's no ifs. That's the picture. Where? Up. That part I believe. I don't know. But you're trying, and you get credit for that. And since it's dark, nobody can tell who that is. Yeah, sure. I'll give you a hint. How can you find where the sun is? Shh. Wait for the hint. How can you find where the sun is? How can you find where the sun is? It's the bright thing. What's opposite the sun? Your. So where is the anti-solar point in this picture?
Behind the guy taking the picture?
Behind that, because that's the camera. He's holding his arms like this to hold up the camera. So right there is the anti-solar point. That's 42 degrees away. It's as simple as that. The straight back angle. Fancy way of saying the same thing. Where your shadow is. All the raindrops that fall, think of it as like a cone. 42 degrees away from that point, all right? Every raindrop that falls through there is going to help make the rainbow. If it's raining right here, 42 degrees away, think of those cones coming out of your eyes. Boom, the rainbow is going to appear here. How far away from your shadow? 42 degrees. If it's raining a mile away, 42 degrees away. It brings up the question, how big is the rainbow? The answer is, you're not allowed to ask that question because rainbows don't exist. Basically it's an optical illusion, or not really an illusion, but an effect that you see. And it's measured in an angular size, not inches, feet, or miles. Okay? Whether it's close up or far away, it's going to always appear the same. If you want to prove this to yourself, try to take a picture of one, okay? Because you stand there, you try to take a picture of the rainbow. It doesn't all fit. So what do? You back up. Well, what happens when you back up? That 42-degree cone goes with you, okay? So the rainbow will always appear to be the same size. Cool story I heard about from the last Summer Olympics. Guy who's swimming the butterfly stroke. You know the butterfly, that one that breaks your back every time, like this? Well, the guy is doing this right in front of his face. He's got the goggles on, and the sun is behind him. Every time he does this, he's seeing two separate rainbows because they're being formed right here. So he had, instead of having both eyes working together, which is how we see in 3D, each of his eyes, since the splash was so close, he got his own rainbow for each eye. That's cool. I'd like to see that. I guess you could do it. Just take a garden hose, hit yourself in the face. Same effect. Hey, try it. Let me take a picture of it because that's even dumber than I'm going to do. It should work. The physics are the same. The sun's behind you. The water droplets are right here. You're going to get the effect. You're going to see the rainbow. My friend got a little clever. After seeing the way that shot came out, he thought, all right, I'm going to be sneaky on this one. Where's the anti-solar point? Yeah, where? Look carefully. Yeah, but it's a big tree, and he's a little guy. He's not little, he's about 5'6". He forgot to make sure his elbow wasn't sticking out. Holding the camera again. Now notice how high up the rainbow is. Notice it wasn't as high up in the other. What does that tell us? Yes. Now, let's make it simple. If the sun is 20 degrees above the horizon, where is the anti-solar point? What? 20 degrees where? Below the horizon. This is called physics, and that scares everybody. When you understand it, it's not so scary. If the sun is 20 degrees up, its shadow is 20 degrees down. If the sun is 40 degrees up, where's the anti-solar point?
40 degrees down.
40 degrees down. All right, let's see if you can handle the tough questions. We're going to throw in decimal points. If the sun is 2.8 degrees above the horizon, where's the anti-solar point?
2.8 degrees below the horizon.
I think they got it. It's that simple. Now, we throw in the next step. This is where it becomes math. You don't need to worry about the math. If the let's make even numbers, because they're easier to, I can do them in my head. If the sun is 2 degrees above the horizon, where's the anti-solar point?
2 degrees below the horizon.
How high up would your rainbow be? Oh, that's a trick question.
44 degrees.
Excuse me.
40. Sorry.
Parents, you didn't see that. It's dark, no marks. What was your second answer?
40.
See, we knocked some sense into it. 42 degrees away from the anti-solar point. So if it's 2 degrees below the horizon, 42 minus 2, you got a tall rainbow. That means the sun is about setting. If the sun is 20 degrees above the horizon, where's the anti-solar point? 20 degrees below. How high is your rainbow?
22.
Yes. If the sun is 45 degrees above the horizon, where is your anti-solar point?
45 below the horizon.
How high is your rainbow? That's a trick question this time. Think about it. What did you say?
Can't see it.
Yes! Why not? Why not?
Because it's below.
It's 3 degrees below the horizon. So, sun's got to be at the right angle. It's got to be below 42 degrees. It's got to be below, it's got to be, 41, yeah, you'll get a little bit. You might even have that. Nope, that's a man-made reading. See, I don't remember what slides. I got so many slides out tonight. Let's see what your next one is. Go backwards. We'll get to that one in a minute. All right, here's how to make a rainbow. You want to see a rainbow when the sun's higher up? Yeah, get a garden hose or get a sprinkler. A friend of mine, unfortunately his cat had died and he buried it in the well there, so he was trying to have the rainbow come into the well. So I thought it was cool. It was a great cat too. So he just used a lawn sprinkler to create his own rainbow. That's all. Now, actually this could have been late enough in the day by looking at it that he might have had a natural rainbow, but you know, he wanted it just right, so he moved to make sure it was in the right position. And that's how you can also cheat. Because a rainbow is one of the most personal observations you will ever see. No two people have ever seen the same rainbow, except in a picture. Now let me say that again and think about it. No two people have ever seen the same rainbow except in a photograph. In a photograph, we can all see the same thing. But if I'm standing out there trying to take the same shot, okay, he's standing here with the hose and he's taking the picture. He said, it comes right into the well. I'm standing here going, nope, lands over here. It's not quite to the well. Remember, it's your eyes. It's your personal cone. So if my cone is here, but he's standing here, well, there's his cone. He's going to see a different rainbow. Every droplet that falls through adds to the rainbow, which we'll see in a minute, but every individual person sees his or her own rainbow. So it is about the most personal observation you will ever see. Nobody else is seeing it. They may see a rainbow at the same time you see one. They got to get their own. You're seeing yours and enjoy it because that is only yours. Let's take a picture, then you can share. All right. Let me see what else I got on this one. Okay. Where's the sun, high or low? Think. First answer, oh, then you thought about it. Why must it be high? High anti-solar point? High sun, low anti-solar point. What do you got there, about 3 degrees? Let's say that's a 3-degree rainbow. Do the math. How high up is the sun? That's going to take you. You're going to need to borrow somebody else's fingers and toes for this. Who said it? Yes! 39 degrees. Perfect. 39 degrees up for the sun, 39 down, leaving you 42 degrees, 3 degrees for a rainbow. It's that simple. You got it. Let's go into the fancy stuff. What was the next one again? Oh, yeah. Double. Look at that. 2 lines. Uh-oh, something's going on. Let's see if we can find the picture. Rainbow. Another. Has anybody seen that idiot on YouTube? Double rainbow. What does it mean? Oh my God. Double. It means you're stoned out of your mind. Double rainbows are not rare. They're very, very common. What it means is that slide's out of focus is what it means. And if my eyes are that bad and it's out of focus, it's bad for everybody. All right. What's happening is there's your 42-degree cone, okay? But sometimes if light comes in at such an extreme angle, it's refracted, it's reflected, but it reflects again before it then is refracted and leaves. 2 reflections inside, it comes back out at 51 degrees away. And that is where you will find your secondary rainbow. And this is all the work that René Descartes did and published in 1637. And we really give him credit for being the first person to identify what produced the rainbow. The problem was, that's great, but that was just the start. We had to wait for about another 30 years for the kid living in that house to grow up. Because he would grow up to produce one of the finest rock albums of all time. Not as a musician, as the scientist that created the cover. No, yours. 2 slides. That's 1. That's 2. Pink Floyd owes everything to Isaac Newton, who grew up in that house. Now, Isaac Newton, if you remember, was the first guy who started playing with light and prisms. And he realized that white light, when you shoot it through a prism, breaks up into its colors. In fact, every individual wavelength of light has its own index of refraction. So the red rays, aren't bent nearly as much. The yellow ones are bent a bit more. The blue ones are bent a lot, spreading it out into the colors of the rainbow. So it had to be a scene like this that got, young Isaac wondering, what is with the color? That he was the one that figured it out 30 years after Descartes first figured out why the rainbow is where it is. So there's your step to it. And that's, was it Woolthorpe Manor, where Newton grew up. Shot taken by Roy Bishop up in Canada, another very famous amateur astronomer. Stolen from him, borrowed, we have permission. What's your next one? Yeah. So to explain what happens, everything possible happens at every step of the way. The sunlight comes in, it hits the edge, it hits the outer surface of the raindrop, some of the light's reflected. Some of it enters and is refracted. At the back surface, some of it continues to pass through, some is reflected. Look what happens with the reflection. It twists it. Here again, some of it bounces off, some passes through and spreads out. And notice what you see on every rainbow shot we've seen. you get red on the outside, blue on the inside, which doesn't quite look right.